by far.
All right.
It's like I don't do that. I don't know.
Last we talked, we were looking at sequences of transitions, instantaneous descriptions. So we had the language A to the N, B to the N, which we knew was context free. We produced a Turing machine with, goodness. I may need to spend. There we go. No, it's 0, 0 star. That's right. And then we went through and we looked at the instantaneous transitions. No, this was for A to N, B. That's what I thought. So we wrote the Turing machine for this. Then we looked at the instantaneous descriptions over the string AABB. These were the transitions. Then we looked at a particular example AABB over that. So we had a sequence of instantaneous descriptions that we came up with.
Oh, yeah.
Did everyone have a copy of that machine that they made in their notes somewhere? If you'll need to refer to it momentarily. Take 15 seconds, refresh yourself on that diagram, the transitions, see if you can remember exactly what they mean, what they did. I'll have them up here as well. So we were replacing a single A with a single X, moving all the way to the right to see a single B, changing that into a Y, and then moving back to find the new leftmost A that hasn't yet been converted to an X. And then we continue to do that process until there are no A's left or there are no B's left. So at that point, we need to validate and terminate. If we run out of A's, then we just need to make sure there aren't any B's left. If there are no B's left, then the string is in the language A to the N, B to the N. If there are B's left, then it is not. So that's what the three main groups were doing. We looked at the instantaneous descriptions, but that won't be as important for this because the next thing we're going to try to do is see if we can modify our Turing machine that we just talked about to see if it can recognize the language A to the N, B to the N, C to the N. Before we fully get into that, let's think, is this language context-free? Do we remember going over this language at all, either as a context-free language or in the context-free language pumping lemma?
Yeah. It's not context.
It's not context-free. Why was it not context-free?
Well, with only one stack, you can keep track of like 2 characters, but not the third one.
Yeah, the 2 characters is from filling up the stack and then emptying the stack. So we can do A to the N, B to the N, add all the A's, remove all the A's to match them to B's. But we also need to match the A's and B's that we've seen to C's. And we can't do that with a single stack. So the interesting question is now, are Turing machines more powerful than pushdown automata or context-free grammars? Since we know those are the same power, non-deterministic pushdown automata. So if you can design a Turing machine that can do this, the answer is yes, they are more powerful. If you cannot, then we can't really say anything yet. But the question is it possible to make a Turing machine for this language? Give that a go for a bit. So we're trying to redesign this Turing machine to accept the language A to the N, B to the N, C to the N, which we saw in the context-free pumping lemma section was not context-free. So we're trying to figure out if Turing machines are more powerful than push-down automata, which they would be if they can recognize this language.
Experiment was Turing seems we don't need to have like a trap state, right?
Correct, yeah, you don't need it to be a total function, yeah, if there's no transition at a particular point for some particular symbol, then we just immediately halt and reject. Are there any other changes that we need to make other than just in group one, adding one or more rules about moving right until we see a C and converting it into some other character that says that we've seen a C?
You need to add something to group two as well.
Yes, definitely some stuff we need to do in group two. At a high level, what things do we need to do in group two?
Skip over the Bs.
Yeah, we need to make sure there's no rule for a B here. We know we've moved past all the Bs. To be in the new state Q2, I made a state Q5 here for reading Bs, because the first time we saw a B before, we converted it into a Y and moved back left to prepare ourselves to be in group two.
Yes.
But now we want to continue to move right, so this extra rule here says now for remaining Bs in this new state Q5, we want to do a no op on them and just move past them. So we're going to rewrite the B with a B, making no change, continuing to move right until we see our first C. Once we see our first C, then we're gonna be back in state Q2 to be able to return to the leftmost A, and it's just to minimize the number of changes that I have to make to this. Yeah,
Do you have to use separate, like markers that it wants to visit, like, can you just do X? Or do you need to do X for A's, Y's, B's?
we need to do X. That's a good question.
Cause I think I got it, and I only did X's.
That's probably fine. Yeah, that should work. It'll minimize the number of rules too. Now we need to start worrying about a rule if we see Y's and a rule if we see, yeah. So what changes do we need to make to group two? What new rules do we need to add and what changes do we need to make? So we know we're in state Q2. When we do this, we should be pointed to the rightmost B, but we have no rules about B's in this group two. Amazed this hasn't turned off. No. So we need some rule. We'll add, I don't want to mess with this, so that it is the last one, so we'll say. We're in state Q2, we see a B, we want to skip over it. So we're gonna say we stay in state Q2. This should still be a B and we'll move back left. So we'll skip over the B's, we'll skip over the Y's, we'll skip over the A's until we see our first X. Then we'll move back to the right, back in Q0 and be ready to do this again. That sounds nice. Any other changes we need to make?
You need to skip over the Z's as well.
Yeah, if we've not just made the first one, then there are gonna be more Z's.
Same with the Q1 or Q5.
Yeah,
Skip over Z's.
yeah. Right, so this will skip over Z's and B's and Y's and A's, getting back to an X. We don't need to worry about C's because there's no reason we'd be skipping back over C's on the way back left. Anything need to change in our validation and termination? So if we're in state Q0 and we see a Y, what does that mean?
We've gone through all the A's.
We've gone through all the A's. If we run out of B's or C's, then we'll break in groups 1 or 2. So the only reason we'd even get to this validation is if we are able to read all of the A's. All right, so we've read all the A's. What do we need to do? We need to make sure that to get to the blank, we go over only X's and Y's and Z's. In this case, you could have used fewer characters here. So we say, if we see a Y, we'll switch to the state Q3. It's gonna move right on all Y's, but now it also needs to move right on all Z's. So. For in state Q3, we read as Z. We want to stay in state Q3. Do a nova and move right. Now, if all of this leads us to the blank, then we can go to our accepting state Q4 and accept. So I think these are the changes we need to make.
If you stay in Q3, could you potentially have an issue with some Y appearing after a Z, or would that not happen?
I don't think that can happen according to the rules in group 1 and group 2. If that were the case, then we would have gone into a halting failing state here. That is a good question, though. Does everyone buy that this Turing machine solves or accepts the language A to the N, B to the N, C to the N? Any questions about the construction or the changes that you needed to make here? So what can we conclude? What is the conclusion of having done this work?
You can represent non-context free languages of the Turing machine.
Yes. We can represent non-context free languages with a Turing machine, which tells us that Turing machines represent or can recognize a more powerful class of languages than non-deterministic pushdown automata, which is intriguing. So does everyone have down what they need with regards to these transitions? There's still no eraser in here. Have to remember to bring that. So there's our conclusion. Turing machines can represent languages that are more powerful than we can represent with either a context-free grammar or with a non-deterministic pushdown automata. And if you want to go into the nitty-gritty proofs of it all, you can see that anything that we can write in any programming language can be simulated by a Turing machine. You could write a Turing machine to solve the CYK algorithm if you had some representation of the CYK algorithm on the tape when you started. That would be an absolutely disgusting Turing machine with way too many transitions. I would never want to design that, and I would never inflict that upon you. But as a theoretical argument, we can see that this simulates any logic that we can write in a programming language. Because we directly write to the output tape as well, Turing machines are not just language acceptors or rejectors. They can also be used as this word that we mentioned on the first day and haven't really mentioned since, this concept of a transducer, which says that we can feed it input and then we can produce specific output for that input. That's not just a yes or no answer. So for instance, we could write binary on the tape, have a number, a blank, another number, and we could write a binary adder for those two binary numbers as a Turing machine, where the answer becomes the third thing on the tape. So that's an example of a transducer, where the output is not just yes or no, it's an actual answer in string form, in some kind of mathematical form that we'll just represent as a string. So any algorithm that you write transforms input into output, and that's exactly what a Turing machine is capable of doing. Questions on that theory? Again, if you're interested in the proof, you can go look it up, but I will not present it in here for sake of time. So I'm not actually gonna have you do this because that would be a little bit painful, but we can at least talk about the design of the Turing machine. How would we do some kind of adding computation on a Turing machine, rather than thinking about just in binary, we need to figure out how we're gonna represent these numbers on the tape. Is there an easier way that we could represent these numbers on the tape than binary?
How?
Yeah. Unary. Unary is what it's called. So having one, you just have basically a number of marks that represent the value of the number. So if there are 10 ones on the tape, that represents the number 10. If there are 100 marks on the tape, that represents the number 100. Very inefficient in terms of storage, but hey, we have infinite memory. Why not use all of it? So unary will be the easiest program. You can imagine writing another Turing machine program that could convert a binary number into a unary number, or a decimal number into a unary number. And that would be just fine. You could do that. But we're just going to skip over that and assume that the numbers are written in unary. So we have x1s. We're not actually going to use a blank. We're going to use a single zero, because zero is not a legal number. The zero is going to be the separating character. That tells us we're going between the first number and the second number. So what would that program look like? We want to be able to basically look at the first number, skip over the second number, and start writing the answer at the end. Or is there an easier way to do that?
You theoretically write the answer at the zero in the middle, but after you like increment it by one, then you would just have a whole string of ones. So you would kind of have to find a way around that.
What if we had 21s and 31s? So we'd have 21s followed by a zero followed by 31s. Idea?
Should we just concatenate them?
You can concatenate them and then take off a one and turn the zero that separates them into a one. Move all the way to the end, turn the very last one into a blank. So much easier than trying to do all the logic to move everything, because it's in unary. So that makes sense, right? If you concatenate two unary numbers, you add them. So the Turing machine is actually not that complicated to come up with at that point. If we're in state Q0 and we see a one, we're just going to skip over it until we get to a zero. When we get to the zero that separates, we're going to turn it into a one. Now there's one too many ones in the number because we've added one from the concatenation. So we go all the way until we see the blank that says we're past the end of the second number. Then we're going to go left, back to the last one, and convert that into a blank. Or convert it into a zero, I guess is what this is technically telling us to do.
Could you just like change the first one to zero and then go until you find another zero, change that to one?
You could
It's
probably be slightly easier.
think about time complexity.
It's going to be the same order, but it's not changing the actual complexity order, but it will give you a constant factor faster.
Unless we compare the terms of x and y's. The first one is x plus y, the second one is just x. If that matters, which is probably.
Doesn't. Anybody have any questions about the logic of representing things in unary and then coming up with a Turing machine that is able to do things like represent the sum of two numbers? So there can be examples of simple transducers. Most of them are much more complicated than this. No questions? Everyone have down what they need? Okay, now we're gonna start exploring Turing machines in a little bit more depth. And try to figure out what modifications can we make to this definition of a simple Turing machine? And what effects did those modifications have on the complexity of the Turing machine, the complexity of the Turing machine programs and the languages that it can accept. So Turing's thesis tells us that a Turing machine is capable of any computation that any mechanical computer can do. Any idea how you would try to show this? Again, I'm not going to go into that proof, but just thinking about how would you try to show this? What would that look like? Yeah, you could break down the aspects of computation and basically say, can we simulate that? A program that does all of those things in a Turing machine? Yes, then we have equivalence. Designing these, so Turing machines are basically meant to be fairly theoretical machines in general and help us to be able to understand aspects of computation because they give us an easy way to simulate programs with an infinite amount of memory. And you can easily manipulate Turing machine programs into other Turing machine programs, as we'll see when we go through what is called a reduction. It's very similar to a reduction if you've done any NP completeness reductions. It's quite similar to that concept. But actually constructing Turing machine programs for this kind of proof is horribly tedious. So what can we do to Turing machines to make them easier to construct programs for, but not change the class of languages that they represent? Does that question make sense? So we know, we've seen this before with regular languages and context-free languages. If we have two different automata that accept the exact same language, then they are equivalent. You can feed, regardless of the input string, you feed them into both of these automata and they come up with the same answer. If one accepts, then the other will accept. If one rejects, then the other will reject. They're equivalent. We can basically do this process and abstract to say what kinds of automata can be equivalent. Can we have a DFA and an NPDA that are equivalent? Is that possible? We can see that if we go through that logic, that a DFA or an NFA is one particular class. It represents one kind of language. And the DPDA, the deterministic pushdown automata, is a separate class because we can define a DPDA such that no DFA or NFA can represent the language that's accepted by that DPDA. There's no equivalent DFA or NFA. We can do the same thing between DPDA and NPDA. So we can construct a non-deterministic pushdown automata such that the language accepted by that non-deterministic pushdown automata is different and cannot be constructed by any deterministic pushdown automata. We can abstractly think about this that says if we could think about every possible automaton that we could make within a particular language, so every possible DFA or every possible NFA, is there an automaton in the second class? So something like, is there a DPDA that would accept that language? If that's true, then the classes are equivalent. And for every automaton in the second class, there's an automaton in the first class that accepts the same language. That's kind of important too, right? We know that we can make DPDAs simulate DFAs or NFAs, but we absolutely cannot make a DFA or NFA that is able to simulate every DPDA or every possible DPDA. There will be some of them that recognize languages that a DFA or an NFA cannot possibly represent. We saw this with the pumping lemma. Now, there's just some class of language. If we're going to go with the NPDA example, for instance, we can use the string A or the language A to the N, B to the N to say that here's an example of a language that cannot be represented in DFAs and NFAs. But we would need a counter argument that says for any DFA or NFA that you could construct an NPDA that simulates it. How would you do that? You would basically say, make no changes to the stack. Right? No stack changes are possible. You have that additional restriction to the NPDA, and then you have a perfect equivalence in the automata between DFA and NFA and NPDA. We can apply this same logic to Turing machines. And we'll see this as a very theoretical argument in the future, that we can attempt to build a Turing machine that simulates the moves of another Turing machine. So the input to a Turing machine is no longer a string in a language necessarily, but it is another Turing machine's construction. If we had a way of taking a Turing machine and representing it in string form, then we would feed that string as input to another Turing machine. And we can ask a question about whether or not this Turing machine can determine what that Turing machine does, or something like this. Right? This is very similar to the concept of a compiler and a CPU. You write a program. Is it possible for the CPU in your computer to simulate the instructions of your program? You just said what instructions you want to be carried out. Can it simulate your program? And the answer is yes. So that is exactly the same concept as a Turing machine simulating another Turing machine. Can we make a Turing machine that figures out what another Turing machine does? We can analyze the simulating Turing machine and figure out what the original Turing machine does, even though we don't have a construction of it. We just have a representation of it on the tape. So think of it like this. You construct a Turing machine, you modify it to put it on a tape, you destroy the Turing machine, you make a simulating Turing machine that is capable of simulating the moves of the first Turing machine. We don't need to construct the first Turing machine or have the first Turing machine, since we can simulate that Turing machine on another Turing machine. Does that make sense? It's kind of similar to the concept of emulation. If anyone has done any emulating of games on your computer, you're basically taking a more powerful machine and you are simulating a less powerful machine on your more powerful machine. Maybe you're simulating a PlayStation 2 on your gaming rig. And because your gaming rig is just that much more powerful than a PlayStation 2, you can actually simulate everything that's going on with the PlayStation 2, which allows you to fake have a PlayStation 2, even though you don't actually have a PlayStation 2. It's capable of doing everything that a PlayStation 2 would do in real time, which when you think about it, is so much more complicated than just having a PlayStation 2. So now we have some theoretical way to determine if two classes of automata are equivalent. As we're able to do this now, we can start saying, what do we want to be able to add to a Turing machine? What would make our lives easier? we can then go look at if this thing that makes our life easier actually changes the class of automata that this Turing machine is. Here's an example. Take everything that we know about a Turing machine, and instead of only moving left or right, we include a stay option that says rather than moving the read-write head, the read-write head can just stay where it is. Is this class of Turing machine equivalent to the simple Turing machine? How would you show that?
Could show that with a simple Turing machine, you can do an operation that would be equivalent to a stay operation.
Yeah, what would that look like? What do you do that's equivalent to a stay operation?
You do your thing, move right, and then no matter what it is, you just move left.
Yeah, you'd have to have different rules for each possible tape character, but that's part of the definition of the Turing machine, right? There's a finite set of characters that can appear on the tape. So for every one of those characters, after you move right, you just, for any of those characters, you do a single move left. Done, you're back where you were. So possible moves are now left, right, and stay. Does it increase the power of a Turing machine? No. There's an actual proof of this in the textbook. If you're curious, you can go look into it, but it does not increase the power of the Turing machine. What this tells us is we can now write Turing machine programs that can move left or right or stay.
Are there more operations?
Yes.
that we can add?
We're going to talk about some of them, and some of them may or may not increase the complexity of the Turing machine, but we'll handle those on a case-by-case basis. So, what if now, instead of having a single track, we are going to parallelize multiple tracks? What this means is we have a read-write head that's capable of reading everything in a bunch of different tracks. So instead of reading in a single character, it will read in an array of characters that come from each of the different tracks. And the number of tracks here turns out to not matter whatsoever. So you can imagine there's just a second track, there are 10 tracks, there are a billion tracks, it does not matter. But does the fact that there are multiple tracks add any additional power to our Turing machine? What do we think? Is there a class of language? Is there some language that could be represented by this that could not be represented with a simple Turing machine?
We can like, one of the tracks we use, like, we can make a Turing machine that moves a specific number of moves. We can do that, and then on a different track, we can move a specific number of moves without modifying the contents of that one. Use the second track.
Interesting. Interesting. Who thinks this is a different class of languages?
Second class.
Who thinks it's the same class of languages? Who has absolutely no idea? Some people who answered for one of the two are answering again. I love that. So the answer to this is actually no. It is the same class of languages. And one way you can think about this, one way that makes intuitive sense to me, is think about, can you simulate a two-dimensional array with a single-dimensional array? Yeah. That one's much more intuitive, right? We have memory with addresses that are in one dimension. How in the world do we even instantiate a two-dimensional array if we only have one-dimensional addresses? We just have to multiply by the rows and then add the columns to be able to just jump to where the appropriate thing is. So it's just a simple mathematical expression to get us in one dimension to where we are in two dimensions with two numbers. Have we seen that before in prior classes? So it's very similar here. If we had a bunch of tracks, we could figure out the length of that track and just kind of simulate each track on the one infinite track. And then we could parse that in the same way. We just have a lot of moving to do to go past everything that's on track one to start track two, etc. But we could do that simulation. So at least theoretically, there's no difference here. Even if there is a huge performance hit if you're trying to do this in real life with a Turing machine. It would be a much grosser program to do this on a single track. But you can take more complicated programs and now you can throw them on multiple tracks. Maybe those tracks represent different things. You can imagine how much easier this makes binary adding, for instance. You throw one binary number on track one, you throw one binary number on track two, and track three is where you're going to write the answer. So much easier. Next possible class. We're going to restrict the tape to only be unbounded in one direction rather than both directions. So now, instead of going infinitely in both directions, it's now only going to go infinitely in a single direction and be bounded on one end. Does not really matter which direction that is. It can be unbounded to the right or unbounded to the left. This is obviously not more powerful than a simple Turing machine, but is it less powerful than a simple Turing machine? No?
I mean, the way I see it, it's like, if you need to put something all the way to the left, you can just shift everything over, it's still infinite, it's just again, a lot more work.
Remember that we have infinite time and infinite memory. We're not concerned about how efficient is anything, we're just determining whether or not it is possible. So I like that as an idea for some kind of proof. If you need to move left for any reason, shift every cell content over by one or over by n, and then you have more space on the left. So surely enough, it is the same class of languages. What if we add extra tapes and extra read-write heads? So now we have read-write heads and extra tapes. So now we're not coupled to be in the same location. When we added multiple tracks before, we always had to be in the same location and read an array, but now we have separate read-write heads that can move separately on multiple different tracks. Is that more powerful than a simple Turing machine? Intuitively, you said, yes, this is more powerful than a simple Turing machine. Who intuitively says, no, this is not more complicated or not more powerful? Who has no idea? I love it. Majority does have it here. The answer is no. You can represent the same class of languages with multiple read-write heads and multiple tracks. It's exactly the same class of languages. It's very, I don't know, I find it kind of unintuitive that that's the case, but there is a proof out there, the textbook has it. You can go take a look at it, and it's pretty amazing that this is the same class of languages.
I don't know, I feel like maybe intuitive isn't correct, but this is kind of like what I'm thinking is
Yeah.
that like. I've tinkered with like circuit boards or breadboards or whatever, and it
Yeah.
feels kind of similar where like, oh, you have like this chip and that chip and like. Are they more powerful, quote unquote? No, they're still all just doing like XOR like 1-0 stuff.
Yeah,
They're basically the same thing. So like for the Turing machines, like you have the same functionality, I guess. and
Yeah.
you're not quite doing something different.
yeah, absolutely. That's good intuition.
I think you could just represent that with more states.
Yeah. How about adding an extra dimension to the Turing machine? So now, instead of a single dimensional tape, we have a two-dimensional tape. And we can now move, instead of just left or right, we can move left, right, up, or down. Here's kind of an image to help you. We have basically X, Y coordinates for where we are in this two-dimensional tape. Yeah.
They have to.
Kind of just like the last example with the two-dimensional, or
Now it's infinite though in all of those dimensions, so you can't really put them next to each other. It was possible before because each of those tracks for any particular example had to have a finite amount of stuff on the tape. So because of that, you can bound that no matter how long it is and put them next to each other. With an infinite two-dimensional tape, we can't really go figure out where everything is because it might end up being a jagged array. It might end up being, we don't necessarily know for sure. If you see blanks, is there other stuff on the ends? Past the blanks, we don't necessarily know.
there's a larger search space, but couldn't you still theoretically try to reach everything, much like with an infinite tape, you could try to just keep going, see if there's stuff past the empty?
We could. In fact, this is not any more powerful than a simple Turing machine. So what's nice about the simple Turing machine is that it is as simple as possible. There are as few options that we can take. So it's important to know the simple Turing machine because why add unnecessary complexity to the options of how we can write our programs if we don't need to? If we can still represent everything that's this complicated in a simple Turing machine, that will make a lot of the proofs easier. It will make a lot of the reasoning easier because those classes are the same. When it comes time to write a Turing machine program, on the other hand, you don't necessarily want to use a simple Turing machine because you're going to be writing so many transitions that it's going to be unwieldy. But this at least tells you that you can start to add some functionality to your Turing machines without changing what they can represent. So you can start to make the construction of these Turing machine programs a lot easier on yourself. All right, I think that's a pretty natural stopping point. We'll come back tomorrow and talk about non-deterministic Turing machines and what that does to Turing machine complexity.
No.
They have staying no matter what.